So counting is familiar to us, just from 0 all the way till 9, and then if we want to count beyond 9, we use 2 digits. This would be 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And it's useful to think of these two digit numbers as counting to 10 and then 0 more. So it would be 10 plus 0, which is just 10. That's why we write it like this. And this, to think of this as counting to 10 once and then 1 more. So that will be 10 plus 1, which is 11, which is why we write it like this. And to think of this as counting to 10 and then 2 more. And we need to do this because we need to use these combinations, multiple digit combinations of characters, because we only have 10 of these, and we use them to write numbers from 0 to 9. So we only got 10 different looking characters, and we need to be able to write all numbers using just these. So we kind of came up with rules to write them down and explained what they mean. Like this would be like counting to 10 and then 3 more, so 10 plus 13, 10 plus 3, that is 13. And this would be like counting to 10 twice and then 0 more, so that will be 10 times 2 plus 0, which is 20. This would be like counting to 10 twice and then 1 more, and that's why it's 21. And the thing is, there is no really good reason to have just 10 characters. We don't know why we just use 10 characters, or maybe we do. I don't know why we use just 10 characters. Because maybe if history had gone some other way, we might have had just 9. So we might have had maybe all of these characters except this. So how would counting have progressed if 9 didn't exist? We can kind of do the same thing that we do here and use the same rules that we use here for writing down multiple digit numbers, and kind of write this down to show that I've counted to, let's switch color, to show that I've counted to 9 once and then 0. So that will be 9 plus 0, which is just 9. So this would actually be 9 in a new system where we had just 9 characters. And this would be kind of like counting to 9 and then 1 more. So that's 9 plus 1, which is 10. So this would actually be 10 in our familiar system. This number in our 8-digit system, base 8 system, let's say, would be 10 in our familiar 10 base system. This would be 11, 13, 14. This would be 14, 15, 16, 17. And again, I can't write this down because what even is this? I don't recognize this digit. So to write down 18 after this, I would probably write it like this to show that I've counted to 9 twice and then 0 more. So 9 times 2 would be 18 plus 0 would be 18. And so this would, this would be equal to 18 in our base 10 system. This in the base 9 system would be this in the base 10 system. And I can continue like so. This would be maybe 19, I think. Yeah, because I'm counting to 9 twice and then 1 more. So that would be 9 times 2 and then 1 more, which is 19. So yeah, this would indeed be 19. 20, 21, 22, and so on. And what I want to do with this video is just introduce you the idea of different bases, systems of numbers with different bases, where we don't have 10 characters from 0 to 9 to write all of our numbers, and how counting would change and arithmetic would change, and what interesting properties would these numbers have with a different base. And before I finish this also, I want to just have a method to switch between these numbers, because these ones are kind of weird. These are very, very unfamiliar. So if you're ever uncomfortable in this side, we can then switch back here to these more familiar numbers. And I just want to have a method written down for doing that. Let's think of how we write down 196 in the base 10 system, in the system that we're familiar with. The expanded form must be familiar to most middle school students, where I kind of think of this as counting to 100 once, this as counting to 10 9 times, and then to 6. So I kind of expand it like so. And to make the pattern more evident, let's write it down like this. Plus 10 to the 0 times 6. So I've just, instead of writing 100 and 10 and 1, I've just written down the powers of 10. So 100 would be 10 squared, and 100 times 1 would be 10 squared times 1, 10 times 9, and then 6. Let's try to do that with our original numbers. So if I write down, say, 1, 2, 3 in our base 9 system, I can kind of think of this as counting to 9 squared, maybe, because I think of this as counting to 10 squared. So maybe this would be counting to 9 squared, and this would be counting to 9 twice, and this might be counting to 1 3 times. And sure enough, if I try to solve this, this would be 9 squared, that's 81, times 1 is 81. This is 9 times 2, 18. This is 1 times 3, that's 3. The answer would be 102. So let's use a different color just to make it more obvious that we have now converted back to our what am I doing? Converted back to our original system, our base 10 numbers, and I can write down any number from the base 9 system to any number in the base 10 system just by thinking of the digits as counting to some power of the base. So if I say, for example, have, what do we use now? If I, for example, have, let's get rid of this. If I've got, say, 9, 2, 4, 3 in the base 9 system, I can write it down like, oh wait, I can't do this, can I? Because this is not a number in base 9. If I have, say, for example, 8, 2, 3, 4, I can write down this as counting to 9 cubed 8 times, and then counting to 9 squared 2 times, then counting to 9 3 times, and then counting to 1 4 times. And of course, if I solve this, it's going to be, let's get out my calculator actually, because I don't want to do this. This would be 5,832. This would be 81 times 2, that's 162, I believe. This would be 27, and this would just be 4. And if we add these up, just plus 27 plus 4, that's 6,200, that's 6,025. So we have a pretty consistent way of switching between these systems.